I'm going to continue there, and I'm going to turn this off, and I'm going to go back over here, and I have my neural networks. This guy, put that down there. So I want to pick up, I'm going to take a sip of water. So the example that I worked with, I gave you guys lots of crazy examples last class. I want to revisit this notion of partial derivatives, and I want to talk about partial derivatives in the context of grades for a class, right? Because I think that this is one of the most straightforward things that you can attach your brain to. One of the questions with our partial derivatives that we're kind of looking to solve here is how much does the change in one small part of this whole network influence the final output? That's that sort of operative question, right? How much does changing, I know I can't do it. How much does changing one input, how much does changing one weight to one input over here influence the overall output of this final thing? So an example that I kind of worked up, and I quite like this one, is that if you take, let's say we take our course grade over here. Let's say I have my final course grade that I'm going to call F. And this course grade is the weight of a third quarter and fourth quarter. And the third quarter is the weight of some summative assessments and formative assessments. And the fourth quarter is also the weight of some summative assessments and formative assessments. And within each of these categories, I have lots of assignments that can contribute to any one of these things. If I wanted to know how much any one individual assignment contributes to my overall changing grade, right? If I wanted to figure out how much will a change in score on one assignment contribute to the change in overall grade for this course, I could actually figure this out. And I think that you guys could also figure this guy out too. You could do that. You would look at this, and how would you say? So I've got some assignment, it's a formative. How would you carry that out? What's the thought process? Tell me a thought process. Yes. Okay, so I find the total number of, so I would want to know like the total number of points. Let's say, yeah, the total number of points, and this is going to be my formative, and this is going to be my summative. So here's this thing. So I'd figure out the total number of points in formative, sure. Okay. And what is this formative going to be weighted by as it goes into my quarter grade over here? 0.3, yeah, 30%. Okay. So if I figure out his fraction of the total points in formative times 0.3, what else do I need to know? This is my fourth quarter grade, and this is my third quarter grade. What else would I need to know? Yes. What's a reasonable amount for how much each quarter is weighted? Let's just say 0.5, 50-50. Let's say it's a semester course, but 0.25 is valid for a quarter. So if I have like its individual percentage of the total number of formative times 0.3 times 0.5, that number will tell me how much a little change in that grade causes a change in my overall score for the class. And you guys do this like all the time, right? This is a lot of emails. Now, that process, that thinking is the chain rule. That is the chain rule. What is the influence of this on the one that came before it? What is the influence of this on the one that came before that? What is the influence on this on the one that came before that? That is the chain rule in partial differential equations. Okay, that is it. That's how we find these things out. And this is straightforward for us because that partial derivative, or sorry, that individual scaling factor is just some scaling. But what if instead of a scalar, this thing that transformed were some function, right? And this is the notion from yesterday. What if that thing were some function? If it were some function, it's still the same process. It's still going to be the same process. And so our objective over here, if we think of this maybe not as grades, but let's say all our individual grades over here are IRIS scores. And the IRIS scores have already been calculated, right? Like our objective is to sort of determine, in this case, if this is an IRIS setosa or not. So we could just make some linear network, some linear multiplications that go all the way through, blah, 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 blah. And let's say I have four things, like I have four inputs. Let's just break these down to 1, 2, 3, 4 inputs that became of this thing, right? So the sepal length, sepal width, petal length, petal width. And you know, in courses, we weren't really weighting these things, but we were kind of not saying that these are zeros, but we can basically, you know, figure this out through, we can say that they get multiplied through as well. And that's going to shift this around a little bit with the calculation, but it's going to be functionally basically the same thing. But let's not super duper worry about this right now. Let's pretend that the weights of those connections are 0 for us. Let's pretend that the weights in between these connections are 0. What we have over here are our 4 data points per iris. I have 4 data points per iris. I can't really change my data points per iris. The iris test has already been taken, right? The iris has already been calculated. I have no control over the iris. What I do have control over, as I try to make this output either 0 or 1, or some percentage in between 0 or 1 that specifies how confident I am about what type of iris you are. What I do have control over is how I weight these things. I do have control over the weights. I can say, hey, you know what? Right now I'm rating formative 0.3 and I'm weighting my summatives 0.7. You know, these guys are 0.3 and 0.7, and these are 0.5 and 0.5. I'm not going to try to change around these values because they're already set, but maybe what I could do is I could nudge this 0.5. Maybe I'll try him at 0.51. Maybe I'll try her at 0.49, right? Maybe I'll give these guys each a little bit of nudge. I'm going to adjust my weighting. And correspondingly, maybe I need to give this guy a little bit of nudge. Maybe they need to go up to 0.5, and this needs to be a 0.5, and this needs to be a 0.2, and this needs to be a 0.8. And maybe that's going to give me the output that I want. Yes. It is basically going to be a trial and error system. This is kind of a trial and error system, but it's a highly sophisticated, mathematically optimal trial and error system, right? Like this is guess and check on some highly directed highway. Yeah, it's a very controlled guess and check is what we're basically creating out of this. Yes, 100%. So you can sort of see that throwing random numbers out in here is not going to give me, that's going to be random in, random out, right? Like if I just change these to different random numbers every single time, I'm not going to get what I want. So what do I need to do to these numbers? Tell me, give me something intuitive. What do I need to do to tell me something here? Let's just talk this out. Right now, let's say I put these things in here and it comes out as like 0.27. And I'm expecting this to be a 1. And then I put in some other numbers and it comes out as like 0.84, but I'm expecting that to be a 0, right? And then I maybe put in like some numbers and it comes out as like 0.03, and I'm expecting that to be a 1. And then I put another one, it's like 0.02, but I was expecting that to be a 0. So right now, these numbers aren't really producing something. So what do I need to do to adjust these numbers? Yes, Mom.
You need to tweak the weights so that the error is minimized.
I need to tweak the weights so that the error is minimized. Yes. Take a moment to think about that. What is my error here? What's going to be my error? Yes.
Well, I guess a naive way would just be like expected minus actual.
Yeah, expected minus actual. What if the error is negative? What if the error is positive? Absolute value, square it, something like that. Yeah. And that's it. That's mean square error. Yeah, we just take the difference in square. Yes. Yes.
Would it be better to leave the error as positive or negative? Just because, like, if it's negative, you might want to tweak the weights one way, and if it's positive, you want to tweak it the opposite way.
That is a very good question. It turns out, and your intuition is absolutely in the right place. We don't really know. These, I have positive numbers over here, but these numbers could have equally well been scalings that don't add up to one, and they could have been negative as well. So I could have some highly complicated negative positive combination of things going on inside of here. And your question raises the really important point of like, what we need to do first before we tweak this is we need to sort of analyze and say, which direction is this going to change the output? We need to know. And which direction it's going to drive, like a change in which direction of scaling this changes that direction and we scale the output. If we can say this is the amount that we need to adjust by and kind of make that adjustment, whether positive or negative, we need to scale this appropriately by that. I kind of jumped around below, but does that kind of make sense? Like we need to know how much a change over here is going to drive a change over there. You can do that for the grades. Yes.
I was thinking like, if you compute a loss function, right, and make that always positive,
Mm-hmm.
it's like kind of becomes negamax. Our goal is no longer trying to get it to be, get the value to be higher or lower to get to the target. Instead of we're only.
I think that's the phrasing that I was looking for. And that's actually what we're trying to do here is we're trying to minimize the actual loss. We're not looking to make it like move in one particular direction. We just want to drive that loss so it becomes less and less and less. And if you almost think of that loss as some sort of like projection in space, as some big, curved space over here, we're not doing this in this highly focused way. We're doing it in this like kind of weird, stumbly, guessy way through tournaments. We're like in a guess that we're going to make an adjustment and then we're going to make another adjustment and make another adjustment and kind of work our way down the mountain to that. Absolutely. But yes, we're trying to make that. I don't know that. I want to go back though and make a little comment over here. I'm not adjusting the scores of these irises. I am not adjusting the scores. I'm not adjusting the grades that the irises got on their 4 tests that they took in this, right? They took one summative, one formative, one summative, one formative. I'm not adjusting the scores that each iris got. What I'm adjusting is like the teacher perspective over here. I'm adjusting the way that I weight each of these individual things that we did. I'm adjusting the weights. I'm adjusting my weighting. I'm adjusting my grade book to make the scores match the output that I want. I'm adjusting my weighting in my grade book. I'm not changing the score that you got on the test, your iris test. Okay. Thoughts on that? Feelings, questions? No. Yes.
Wait, so, the weights, they didn't necessarily have to add to one, so like, you could just tweak the weight of one branch.
Absolutely. I could just tweak the weight of one branch. So here, yes, I started with these random values over here, but I could just tweak this guy. And if it turns out that I need to like make this like a negative 0.5 and this a 1.7 over here, and that's the thing that works. These weights, they're not fractions. These are really just like in the actual operation of this thing, they become scalar scalings. Yes. Was that a question or a good stretch? Yes. How do you know which way to change the weights? That is the question. How do we know which way to change them? That's what we need to do. That's what we need to do. Okay. So the answer is going to be, and I'm just going to sort of tear this out. I can draw that. Towards the end of this guy, on page 70, whatever, and I skipped lots of pages over here. But towards the end of this, we get into this thing that I'm calling training. And the process of training is the process of the teacher going in and adjusting the weights of each of the assignments not the actual value, not the score that you got on the assignments. It's me going and playing gradebook weirdness to give you a different grade over here and finding out some loss function. There are two commonly used loss functions. One is mean squared error, and then there's another cross entropy. Mean squared error is the one we can look at right now, and that's basically what we've described over here. So if we were to do this for a batch of things, we tend to do it across the average of like a tournament, right? Across the average of the tournament, we would get the average, but we don't really need to do the average if we're just looking at one in isolation. We can say that the value for one single value in operation is the value of the observed data point, the ground truth minus the expected data point. So observed minus expected squared. And this tends to accentuate large differences and sort of de-emphasize small difference because it uses a scaling factor. So we're going to take this loss function. And the next thing that we need to bear in mind is that there are other loss functions. We do it in batches. I feel weird that I wrote all this stuff and then I didn't. And then there's this cross entropy loss, which looks like a lot, but it's actually used for binary classification. So this is a binary classification loss function that we'll get into as we get a little bit deeper in the weeds of these. We don't really need to look at this too much. I have some partial derivatives over here. But what I really wanted to say is that when we have this loss, right, we have this loss value, what we're going to do is we're going to go back afterwards, and I have my network of my, 4 things over here. And I've got weight, weight, weight. I have some loss. We're going to choose something known as a learning rate. We're going to choose a learning rate. And that learning rate is going to be some highly scaled version of this loss. So it might be like 1/1000th of the loss. And what we're going to do is we figure out the partial derivative of every single one of these factors that influences that final value, right? So we figure out all of the influence that everybody's going to have on that final input, and we're going to give them an all is sort of like ratiometrically appropriate adjustment. They get 1/1000 less of their impact on that. And if we know the partial derivative of each of these guys, so if we're thinking grades, it's always like a, a +1 over here, but turns out that could be negative. If the input is negative, like it could have a negative influence. And so the sign will get sorted out. The sign of all of these guys gets sorted out just by the math of it. And what we're going to do is we'll say weight minus 1/1000th of the loss. Weight like minus the partial derivative times 1/1000th the loss. The weight, and each of these guys will get scaled down by amount that corresponds to their partial derivative. That's going to be one tiny fractional step that we know is going to adjust everybody in the direction that they need to go. So the direction that everybody needs to go is going to be different. It's going to be sorted out by the values of their inputs. And I can just say, trust me for this right now. Trust me that the value of the input will determine which way it needs to go. They'll get scaled down a little, and that's going to step us one little bit closer to the answer. And by doing enough batches of this thing, in much the same way that the genetic algorithm kind of found that right answer, this thing is going to find that right answer. Do you want me to say that again? Okay. Kind of in the way that the genetic algorithm ran tournaments, and it improved a little bit every single time. If we run batches of our inputs in here over and over again and say, what are you? What's your expected value? What's the loss? Scale that loss down a little bit and scale everybody a tiny fraction that corresponds to your partial derivative amount. Scale this guy a little fraction. These guys are going to start moving in all kinds of different directions to sort themselves out. They're gonna be like little minions that just know what to do because of the function values that they have inside of there. And they are going to work their way into an answer that sort of maps the solution space appropriately. That's the trust me phase of this for right now. Yeah. Okay. Tearing right along. So where do I go from? Let's say this. Let's go here. Let's go to the different. I'm going to go to this partial derivatives problems thing. So I want to introduce some nomenclature over here. The first thing is going to be this. When I use superscripts, this is going to be layer specific. And I want us to look at these problems. So this is going to be the things, guys, that I'm saying here. Let me put this up. This is the partial derivatives problems. So I've got a handful of people in here right now, but if you can join me with this, my goal is to kind of work on this together. So on partial derivatives problems, this is in the neural networks folder, partial derivatives problems. It's in development. It's not really where I want it to completely be, but it's going to be enough to get us through this for right now. Okay, so if we can go over to this partial derivatives problems, we've got, thank you. I love how many people are along right now for the show. So you can look at this. So as you're looking at this, maybe you see that there's this A0. I'm referring to layer 0 right here when I say this. This A0 refers to a layer 0. Okay, yes.
And that's not the 0 is the first wave, like first layer that's after the wave. So it's not the inputs.
It's not the inputs, right? So I've got my inputs over here, assuming I have some inputs, and my network over here is basically going to be like input, weight, summation, transfer function, output. It's like the simplest single node. I just want to have like a one layer, one neuron network right here is what I'm expressing. And we typically work from left to right, where if I have some layer, I'm going to have layer 0, layer 0, and then these are going to feed into layer, 1, and then these might feed into all these connections would feed into layer 2 and stuff like that. So that superscript is referring to which layer I'm living in right now. Okay. And my output in this case is just it's just a single layer over here. Okay. There's another thing that we've got. Z. I'm going to use Z a lot. So when I say sigmoid, do you know what I'm talking about when I say sigmoid at this point? Yes, love it. Great. You should know what I'm talking about when I say sigmoid at this point. If you don't, that's a thing that you should be aware of, okay? But when I say sigmoid, you're like, okay, I get that. That's good. Which is this function over here that maps values that are negative to things. Could be a rough approximation of the probability. Outputs between what and what, 0 and 1. Okay, the next thing that I've got is Z, and I'm using the nomenclature of Z a lot as well. When I say Z, I'm referring to the sum of the inputs, the weighted input sum, the weighted biased input sum before activation. Okay, so in this case, my Z is going to be input 0 times W0 plus bias 0, which we're treating as 0. That's my Z right here. And so the question is, symbolically, what is the derivative of sigma with respect to Z? Well, in order to do that, we first need to have sigma. Can you tell me off the top of your head? Oh my God, making me so happy. Thank you. Okay. I am not going to spend the time doing this, but I will tell you that the derivative of that, and I trust that we all can do derivatives, or I'm hoping that you can, is sigma of z times 1 minus sigma of z. It's actually a pretty straightforward derivative when you get right down to it. Computationally expensive, but not like crazy to look at. Okay, great. I like how many people responded to that. I feel like this, I need you guys to internalize these things. Alrighty. If this neuron uses sigmoid activation function and the weighted input evaluates to negative 0.5, what is the actual value of this thing? So, the partial derivative. Now remember, we said the partial derivative is something that we can think of. In this case, it's just basically the single derivative because this isn't a multivariable function, but it's the derivative of this function with respect to z, right? Substituting, yeah. So if we think of multiple axes and this sort of plane on which this thing is defined, and right now it's a ramp, it's a slide that is the same for all values in this dimension. And we've got this slide over here. Intuitively, should this number be positive, negative, zero? What do we expect this thing? Sigma of z times 1 minus sigma of z. What is the maximum value that sigma could ever have? 1. Okay. Are we likely to get a value of it? Thank you. If we're not. So sigma of z times 1 minus sigma of z is probably going to be positive. That is your gut check right here. What is the value? Somebody tell me. Somebody with the calculator that does yes. 0.225. Does that make sense? Okay. 0.225. I agree with that. So my input space over here, right? I've got this thing. That's a horrible sigmoid. He's showing up at negative 0.5, and that's just kind of before we're ramping up. We're not near the maximum slope, but we're kind of getting there. So that's a 0.225 slope to me. We kind of max out at about a quarter, and then it stops. Okay, sure, 0.225. I agree with that. Carrying right along. Okay. So this next question is kind of getting at this notion here. So what I'm really asking is, do you believe that the value of the derivative of this function is, or let me put it this way, symbolically, the derivative is functionally equivalent, right? The function is always the same, but the value is not always the same. And that's true for any nonlinear function, right? The value is not always the same of the derivative. That's what makes us nonlinear. And so I guess I'm trying to convince you of some nonlinear function with this. What is the partial derivative? Or sorry, what is the value? Oh, it's not even that. Oh my God, look at this. This is straightforward. What's the value of z? What is z? I just said what z is. Tell me what z is. The weighted inputs, right? Z is our weighted inputs, weighted biased inputs. So I've got a bias of 0 input for weight negative 0.333. So what is z? Negative 4/3. I agree with that. Okay. So z is negative 4/3. Awesome. What I want you to see over here is this weight is negative. So weights aren't necessarily all adding up to 1, right? These weights, these are just linear kind of scaling functions going on over here. My z, I've got some mapping. I'm going to draw a better sigmoid over here. That's wrong. inputs, right? That's annoying. It's there. So what do we expect this number? Z is negative 4/3. What is sigma of Z going to look like? Tell me where sigma of Z is going to be intuitively. It's going to be near 0. Near what? Greater than 0, less than 0. The sigma of Z is probably about what? Near 0. It doesn't drop off that quickly, but this is less than 0, greater than or less than 1/2. Less than a half, right? So negative numbers map to less than 1/2. Negative numbers map to less than 1/2. Z is 4/3. I'll let you guys actually figure this out. Here we go. So what is the partial derivative? Here's the question. What is the derivative of sigma with respect to Z for this input situation? How do we figure that out? What's my formula? The reason I'm having you repeat this is because what do you think you are going to need to code up in your neuron? Yeah, the derivative. You are definitely going to need to write this function in your neuron. Your neuron needs this. Your neuron needs that. Yes. You are going to need to have the function. You're going to need to have this function somewhere out there. And you're going to need to have not exactly this. You're going to need to have something very close to this. You're going to need to have the derivative of the activation function with respect to this. That's some different. Okay. So what's our value over here? Negative. Wait, what? 0.6. Thank you. 0.165. That makes more sense to me. Yeah. 0.165 makes sense. It's kind of small, negative 4/3. The derivative is 0.165. The derivative being 0.165 kind of suggests that that slope is real small. That's down there. He's definitely below 1/2. We're way down here. Okay. So what this is saying is that because this input is already kind of negative, and it's going through the sigmoid function, and we're going to have some loss function over here, the amount that this weight would get scaled is going to be actually different than the amount it would have been scaled given other input conditions, right? So given input conditions that make this Z evaluate to 0.5, and given input conditions that make Z evaluate to -10, and given input conditions that make Z evaluate to all of these different conditions are going to mean that that will be adjusted by a different amount. And this is kind of what I'm saying when it's all going to get sorted out. Like the amount that we're going to adjust this in our sort of guess and check is going to be adjusted by this partial derivative. Yes.
So how much we're gonna adjust the weights is depends on the derivatives.
Yes. How much we're going to adjust the weights, how much I'm going to adjust this weight is dependent upon the derivative that's sitting after this. Because how much influence this weight has on the overall score is dependent upon the derivative that comes after that. So how much adjustment we make to this depends upon the output of that Z function. That's the chain rule. And it was 1 when everything was just scaled linearly, but it's not scaled linearly. It's scaled. Yeah. So yes.
Correct to say that what our goal is to get D loss over D weight.
Yes, our goal is D loss, D weight. That is exactly our goal. Our goal is D loss, D weight. If we know D loss, D weight, we know how much to adjust the weight. Some little micro scale of it. But if we know D loss, D weight, we can adjust it. And if we know that this weight needs to, that's where the sign gets sorted out. D loss, D weight. Oh, needed to go up. There we go. It's going upwards. Yeah, we know what D loss, D weight is going to end. So that is our goal. Yes, I love it. Take a moment. Okay, so here we go. Now we are cooking with gas. So ReLU, when I say ReLU, what am I talking about? Wait. This guy and that one, the ReLU over here, that's sitting where who just was sitting? What was I using in the place of the ReLU before? Sigmoid, thank you. Yes, I was using sigmoid there. Okay, so I was using sigmoid there. Now I'm using ReLU. What is a ReLU? I don't really know how to say it. What is the slope of a ReLU function? 0, 1. Oh my God. Is this an easier derivative to compute? You better believe it. Is this a faster derivative to compute? You better believe it. Yes. Is realizing that we can use these linear functions in the way that we can effectively use them versus getting off of sigmoids. Like neural network training was hooked on sigmoids for like 20 years. And then all of a sudden we figured out a way to make ReLUs work. And this is why we're at like chat GPTs and images coming out of everywhere, because the speed is substantially faster when you don't deal with taking 50,000 sigmoids every single time, right? You are bound by computational constraints that you cannot believe if you're just pumping this through sigmoid depths. Yes, sigmoid is expensive, even in a lookup table. So here we go. So with my ReLU over here, so what are my derivatives? Tell me, what are my derivatives? Zeros and ones, yeah. Now the question that I didn't ask, and the question that is sort of implied over here is my math purists will recognize that the derivative at 0 is actually what? Undefined. So by convention, the derivative at 0, we just substitute it because we're going to use a condition. This is a conditional statement, right? So it's a conditional statement, and we'll just include 0 to be in that conditional statement, and everything's just hunky-dory. So great. So what's my partial derivative? What is my, I probably should have said my d ReLU over here, my derivative of ReLU over dz, when these things, when this guy is here, okay, if this is -4, so if my x is -4 and w is 1, what's this guy's derivative right here? 0. Yeah. Or this one is positive. So ultimately, having a 0 in here is kind of bad news. That's kind of unfortunate news. And if you were to look at dl over dw0, and if that comes out to be 0, turns out that really no amount of like little stepping is going to fix that problem. Like that's a broken system. So this is why we have something it's called the leaky ReLU, and the leaky ReLU gives it a really, really tiny scaled version or here. So instead of 1, 0, or like 0, 1, it becomes like negative, or it becomes like negative point. Say that again. 0.1, yeah, thank you, 0.1. But not even 0.1, like 0.001 or something like that, or 1. And that actually solves the problem. The leaky ReLU was the guy that's the hero of the story in all of this. Because this gives us something that's differentiable for values below 0. Yes.
That sort of all of your weights with ReLU out.
Yeah. Yeah. Not really. Not really doing what we wanted it to do. Great. Okay, I like this internalization. Okay, so here we go. So now we're kind of getting into here. Okay, so now let's talk about this. And this is going to really require us to tap into the mindset that we are not adjusting this, we're not adjusting the scores that the irises got on the test. We're adjusting how we weight the scores of the irises, right? We're not letting them take it. There are no retakes. The iris took a test. We have to scale this differently. We're gonna change our grade book to make that. We're not gonna let them retake the test. So here we go. So the question is, what is the partial derivative of z with respect to W0? Yes.
Introduce like less nonlinearity.
It is less, I don't know if it's less nonlinear, I don't really know how you quantify less, right? Like, it's still nonlinear, if you have a piecewise function, that's still nonlinear. And if you were to superimpose lots of these piecewise functions, you can create very, very complicated nonlinear functions. You still ultimately need, in order to get this kind of like smoothed out, at the end, we don't totally escape the signal layer Canning function. The activation layer at some point is gonna need to be ruled out, right? But it allows us to have a fast piecewise approximation of functions that is okay. Yeah, okay, I love this. I'm feeling kind of good about this, not gonna lie. Okay. So I have my two, like I got my steep slope and I've got my less steep slope over here, right? I have two things that I can change. I can do my switchback down the mountain this way, or I can go straight down the hill this way. I can choose to say which derivative am I going to look at? Am I going to look at the W dimension that goes way down, or am I going to look at these X dimensions over here? I want to adjust my grading. So how does my output change with respect to the way I weight this test? How does my output change? How does my Z change? Yes. It changes by X0. Yes. And so people who haven't done partial derivatives yet, this is going to be a little bit weird, but hopefully we can kind of look at this as the entry level partial derivative. We didn't differentiate, normally we would have said, oh, the derivative was this guy. But when we look at it in the opposite plane, sorry, because you don't matter in the derivative, not that you don't matter, but you don't matter in the derivative. It turns out that, yeah, the derivative just kind of took this guy out. So our partial derivative please move. Our partial derivative with respect to W0 is actually X0. It's the input. It's the score on the test. Yeah. Yeah, you're basically treating X as the constant. X is a constant over here. Yeah. It's weird. It's weird. It doesn't feel right. But X is basically the constant over here. So my formula, X0. That's it. That's the partial derivative formula of this guy. Now, what we're looking for, right? When I say the derivative of Z with respect to dW0, this is talking about how the output of that changes as I change my weighting function. As I'm tweaking the grade book, how does the score that this iris got on her exam change? And the reality is that I don't just care about the output of that. I care about like the output of the final grade book. I care about how this changes your overall grade way down the line, right? I don't just care about this function. I care about all the others. And so to figure out the overall impact on the entire system, what did we need to use to get that? How did we do, what sort of operation did we do to find, when I was looking for the influence of like the introduction section of my paper on my overall grade book, I used the chain rule. So this thing is going to be the component of the chain rule at this point. So the chain rule in figuring this out is going to have to go through dz dw0, right? And then we know after this, sorry, this is kind of chicken scratch, but I have dz dw0, and then after that I had d whatever, let's say d sigma dz, and then after that I had d loss d sigma. And this is effectively the thing that's describing how W0 influences the loss. That will describe how W0 influences the loss. And if I can take this quantity and take some really, really small fraction of it and say W0 minus that really, really small fraction that influences your overall influence on that output, I can make a little teeny nudge. Yes.
I don't know if you're gonna talk about this later, but let's say I have like another X0, another.
Mm.
Things X1 with W,
Mm-hmm.
but I'm trying to take the partial derivative with respect to W0.
Do it. Sorry, is it another? I missed that. Are you having other neurons down here or other inputs? Yeah, other inputs. So formulaically, this is exactly the same, right? So formulaically, this is going to be the same. Computationally, it's going to evaluate to different numbers because of the presence of the other numbers being part of the soup at like this stage of the game, right? But back over here, yeah, I mean, that's basically it. I like that question. Your intuition is in the right place. So here we go. So to repeat, I just erased this, but what's the partial derivative of sigma with respect to W0 at this point? What's my partial derivative of sigma with respect to W0? Take a moment, talk to your neighbor, take a moment to digest this. I need you to know this. I don't need me to know this. I need you to. I need you to be like, okay, the partial derivative. What is going to be the partial derivative of sigma with respect to this guy? And what's the formula? And for can you give me a formula without using these? Ooh, can you make this formula without using this? No Z's allowed.
Yeah.
Sigma of this yeah, it's one minus sigma of I do the that's I0. Yeah, we'll call it I0. We'll call this I0. I0 works for me. All right. How do you feel? Any thoughts on this thing? Let's say it again. With doesn't really matter. What's it with Z? With Z, it would be. I'm sorry, I didn't quite hear that. D sigmoid DZ times DZ DW0. Absolutely. So, absolutely. I agree. Now, D sigmoid DZ, that's a sigmoid, yeah. D sigma DZ could be treated as, right? It would be sig of Z times 1 minus sigma of Z. And the chain rule, if we were to apply the chain rule over here, this would effectively say I0 W0 times sigma of Z times 1 minus sigmoid of Z, which also could be I0 W0 sigmoid of I0 W0 times 1 minus blah, blah, blah. Yes.
Shouldn't it just be I0, not W0 for the outside?
Oh, geez, Louise. Sorry. Wow, you're not wrong. Okay. We just did this. We literally just did that. So, yeah, Eric's point. So hopefully you can sort of see what this would look like and feel like, but I would argue that the formula is exactly the same, right? The formula of d sigma dw0 is exactly the same. The approach computationally is exactly the same. But could I actually figure out what that value is? Could I compute? So here I'm saying, oh, geez, I'm not reading what I wrote. What's the formula? What's the formula in this case for the partial? So it's the chain rule, right? This is the chain rule. So the fun fact is that I've got some output y. I'm not even considering the loss over here. I've got some output. And when I show this puppy over here, there's this implied z value that lives inside of here, right? It's a little neuron that has his own little z inside of it. He has his own little sleepy z's in there. And in order to, that is going to drive me bananas. And there's probably some setting that d sigma, dz, dz, dw0, right? That's this guy. D sigma, dz, dz, dw1. And these guys kind of live together over here. They live together, and these two work together to define how a change in them could define a change in the output over here. Yes.
So my
Okay. Okay. So, to that end, if I have a value, so that's my formula. But if I actually have numbers like this, if I have numbers like X, W, B, can I actually figure out the value of this thing? What do you think? Could I compute d sigma dw0 right here, given the information on the page? Can you give me a number for d sigma dw0? Yeah.
Don't you need X1 and W?
You do need X. Yeah, you do. Take a moment. That was my question. That's my trick question. Why do I need that? Olivia, why do I need that? Is it? Okay. Take a moment to say that to your friends, to your next door neighbors. When you calculate sigma, we have to calculate sigma of z. You need to calculate sigma of z. What's z? The weighted sum.
X and W.
Do I have a weighted sum with the information up there? So this problem cannot actually be solved. So the reason I point this out is the reality is we can solve this problem. We will solve this problem. We do solve this problem. But this is beginning to think about the structure of what we're going to actually do here. Okay, let's take a moment out of this whole dz, d sigma stuff and talk about, like, boots on the ground. What is this thing going to look like? I've got this neuron over here, right? I've got these neurons and I've got all kinds of partial derivatives going on within these neurons. We know that on one side of these partial derivatives over here. We have one thing that seems to be part of every single partial derivative, which is what? It's that d loss, d whatever, right? That final value seems to be part of all of these partial derivatives. And the same process of figuring these things out can be applied backwards. So computing the partial is this product of this guy and this one and this one and the sum of these times the sum of this one times that, and it's gonna work its way back. So what we're gonna wind up doing with our neurons in our networks is we're gonna take, like neural network one, we're gonna take all the inputs and you're gonna multiply them through and you're gonna produce some output, right? And then we need to make some adjustment that says, look at our loss. This is what training is. We're gonna look at that loss. And we need to then figure out what the partial derivative is for each of our individual weights at this pass event, right? At this singular pass. Because that whole combination is going to change from pass to pass to pass. So we're going to run through this way. And then we're going to go back and compute the partial derivatives for all of every single weight in this thing. And then we're going to give them all a little bit of a scale, and then we're going to do it again. Okay. So as we go forward, compute the layer, we compute the layer. It sounds like a lot, but it's just a loop, right? It's multiply input, produce output, multiply input, produce output. It's just a loop. In order for us to start working backwards, what do I need to retain? What do I need to know? What also is going to be part of this neuron class? Let's just start hearing ideas. What else do I need to drop? What might I need to know? Yeah. I would need to know the partial derivative of each weight. Partial derivative. Yeah. That's kind of there. Almost. Yeah.
Does back propagation optimize like the combination of partial derivatives, or does it just do the ones that are maximized, like for each individual?
So it maximizes it in the sense that, like, they're going to be scaled by the way everybody is scaled uniformly. At least for us, for right now, everybody's getting the same scale. They're going to be scaled by the learning rate. So however much influence any individual weight has on that final network is going to be adjusted 1/1000th in the direction of whatever the sign is coming out to be. So what we're going to need in our neurons is these neurons are going to produce, every neuron is going to produce an output, right? We can figure out what the output is. We could look at the output and we could compute dz, d weight. We could figure out dz, d weight and just store it at the time. That's straightforward. We could compute for that neuron, we could compute the deactivation d weight as well if we really wanted to store that. So basically though, and I have a sneeze. Sorry. Oh my God, I'm so sorry. What each neuron is going to need to know is it's going to need to know its basic, its derivative, right? The derivative of the output with respect to each of these weights. And if we have that, we can work our way back. Derivative with respect to your weight. Okay, great. In my next layer, I'm like, okay, hey, look to the guy that is one down the line. What's their derivative with respect to their weight? I'm going to reference that, and I'm going to multiply these things through, and then I'm going to hold on to my derivatives with respect to my weight. And then I'm going to go back another layer, and I'm going to be like, okay, layer before, what was your derivative with respect to that? And then I just multiply one extra term on side in here, and I can just figure this thing out the whole way through. I can know everybody's partial derivative. That's going to allow me to figure out the partial derivative of everybody. I make an adjustment accordingly, and then we put numbers through and we do it again, get the output, figure this thing out, work our way better. So that's our sort of end game. That is the systematic process of this. Take the tournament of irises, put them in there. Feed a value out, figure out a loss. Let the gradients, which are changing with each individual value, be determined systematically. Adjust them all a little bit. And then get ready to do this again. Take a new set of inputs, run them all the way through. We have to figure out what these derivatives, what these partial derivatives are going to be, because the partial derivatives are kind of dependent upon the actual input values, as we're seeing over here. We're going to multiply these things back, multiply back, multiply back, multiply back, all the way through. And hopefully, in the same sense that our genetic algorithms kind of began to converge on some actual solution, this thing will begin to converge. And the fact that they have converged is this sort of real proof. No, I'm sure there's some proof out there somewhere, but that's the mechanics of what we're doing. Thoughts on that? Somebody give me a question. Stunned silence. Okay, it's actually not that crazy if we think about it. Like the actual process is kind of not that bad. So the chain rule is this algebraic expression of these things, right? We need to look at this. My d sigma dz over dw0 is what is d sigma dw0. That's it. That's the chain rule. Oh, expressed using I already made you guys do this one, right? So you could go through, and in theory, you could punch all these values into here. You could substitute z. I guess really the thing for me that I care about the most is what's z. If I say what is z, do you know what z is? Yeah.
W0 times x0 plus x1.
Okay, excellent. The partial derivative of W0, or sorry, the partial derivative of z with respect to W0 is going to be the input. Knowing that the partial derivative is the input, knowing that we're tweaking the weights, we're not tweaking the values. We can't tweak the values, but we can tweak the weights. Knowing that ReLU isn't really differentiable for values less than 0. And we're going to start with a lot of sigmoids. So we're going to work off the sigmoid at first. We're not using biases. Biases would be the same. It would be functionally equivalent, but like I'm throwing enough at you right now. Let's avoid biases. And that's basically that's the show. And the final question, I guess, for everybody over here is if I have multiple neurons over here and I have some Y value, what is, and here's my W layer 0 weight in layer 1, A1, A0. Take a moment. Can you hammer this out with the people sitting next to you? Can you figure this thing out? What is the chain rule? When I say this A1 and A0, what's living inside of there? What is the full chain rule partial derivative of W0? I want D final sigma, D sigma 1 over dW0. I should use, really, I'm looking for D sigma 1 over dW layer 0 weight 0. That's what I'm really looking for. How do we get that? D sigma layer 1. Random guess. Where do we start? Talk to your neighbors. You can talk this out.
Yeah, so it's nature. It's like the hardest. Please, just see what I'm just.
It's a 1, but it looks like a prime. That's a 1, sigma 1.
Take your try.
Oh, yeah, it's way too.
You're finding B, not sigma 1 over B. I know, yeah, that's good. B sigma 1 over B 1 0. Did she write that one, right? What?
Feelings on this? Does anybody have a feeling about this? Tell me what you're feeling. What is this even asking? Somebody give me words. What is this in spoken language? What is d sigma 1 over dw00 actually represent? Yeah, or yes. Sorry, go ahead.
Rate of change of the sigmoid function in layer 1 with respect to the zero weight.
Okay, I like that. The rate of change, the way that the rate of change of the sigmoid in layer 1 with respect to the rate of change of with respect to the change in W0 in layer 0. Olivia, what were you going to say? I'm basically the same. I'm curious to hear basically the same thing, but what is how much a shift in W0 makes a change in what? The final signal. Okay. How much a shift in this W0 causes a shift in the final output? We need to multiply this W0 by some things along the way to figure that out. What are the things that we need to multiply it by? What are the functions that can have that we're going to encounter? What are the little whistle stops that our choo-choo train goes through along the way? What's the first stop W0 goes through? Who's the first function W0 goes to? So before it goes to sigmoid 0, he goes to somebody else. Z, he goes to Z0. So W0 goes to Z0 first. So I need DZ0, DW00, right? After Z0, who do I go to? D sigma 0, exactly. Superscript or subscript? I was using superscript. Okay. So what do? I add those together? Multiply them together. Thank you. All right. Then this thing goes to what? Z1. C1 with respect to, wait for it. Yeah, so that kind of gets a little bit funky and it's a little weird. So what we had over here was we have if I work, I'm going forwards. But it could just as well have been done backwards. DZ 0 or DW, just call it 0. D sigma 0 over U D. What did I have? Z0. But DW0 over D sigma 0, that doesn't really make any sense, right? That's just one. That's not really a real transformation over here. So what we have going on here is for the benefit of keeping this present, we'll say DW0U. DZ1 DW01 D sigma 1 over D. Sigma 1 over DZ1. So it basically just becomes multiplied back all the way through. We can create this. Sometimes we're going to call this Y over here, Y hat A. Sometimes you might have this. The reality is that these guys over here, the rate of change of the activation function with respect to Z sometimes will be referred to as DA, DZ, deactivation, because right now I'm calling this sigmoid, but if I say DA, DZ, that could be the activation of sigmoid or a ReLU inside of here. And this maybe makes a little bit more sense to say like the derivative of Z with respect to that activation function that was going inside of here. So I think we've kind of hit the wall. Fun fact, you don't need to know any of this to do neural network 1. Okay? But you need to know the storm that's brewing in like Iowa right now, right? And that is on our horizon, coming down in a few days of wind away. And there's no expectation that you work on that over break. But to the extent that you can incorporate like classes and stuff like that are kind of preparing yourselves and thinking along the way, like, oh, I might need to store this thing. Oh, I might need to make a function that computes the derivative. That kind of stuff is going to be to your benefit. Okay, but definitely not necessary for right now. I'm going to stop this record. I'm going to stop the share. Stop.